Welcome to Lecture 21B entitled Divergence and Curl of a Vector Field and also Vector Identities. The material for this lecture comes from reading Assignment 4, Sections 1.8.5, 2.7, and 3. The objectives of this teaching module are to compute the divergence and a curl of a vector field, making use of the material which was presented in Lecture 21A. Revisiting Lecture 21A, that is basically using the definitions of divergence and curl to calculations that we had started with looking at a 2D vector field. And then lastly, working with vector identities. The concepts and visualization skills, 2 items. First of all, an intuitive understanding of the divergence and curl of a vector field, and the interpretation of specific vector identities which are used in mathematics to simplify calculations typically. As usual, the second slide is just a summary of the slides to follow, and so we'll just move on to the next slide. Alright, so this is essentially a slide summarizing the 3 basic, or what we call primitive vector operators, that we are now basically familiar with. We know basically what we mean by the gradient of a scalar function. We also now know what it means to take the curl of a vector field and the divergence of the vector field. And so in the second column, basically, I've written everything out in specific form, phi being the scalar function. And so what we're doing is we're taking a scalar function and producing a vector, and the components of vector are just the partial derivatives of the scalar function with respect to x, y, and z. When we take the curl of a vector field, then typically we can write it in a determinant form, that is a matrix where the first row are the unit vectors in Cartesian coordinates, second row are the partial derivatives with respect to x, y, and z, and the third row are the components of the vector field f. And if we take the determinant, then we end up with this expression for the x hat component of the curl of the vector field. This is for the y hat component, and this is for the z hat component. So in effect, the curl operation takes a vector valued function and it basically converts it to a different vector valued function. And the interpretation of this vector we'll talk about again, even though we've discussed it in Lecture 21A. The divergence, basically, we're taking del operator and we're operating on the vector field f, but in this case we're using a dot product, not a cross product. So in this case, partial x operates on fx, partial y on fy, and partial z on fz, and we end up with this expression here. So what does divergence do? It takes a vector valued function and it produces a scalar function. Alright, so let's do some quick example calculations. So compute the divergence of the vector field f. You're given this as the vector field. This is the x component, y, and z. And so if we're taking the divergence of this vector field, the del basically is this vector operator, partial x, y, and z, operating on the vector field with x component x sine y component z squared cos y, and z component e power z x, y. And so we take the partial of x, operate on this term, partial y operate on this term, partial z operating on this term, and these are the 3 expressions that you see here. And because it's a dot product, these all add up. If you take the partial derivative with respect to x, y, and z, we end up with the corresponding terms that you see here. Let's take the same expression now and compute the curl of the vector field f. In this case, we would basically put it into typical determinant form. First row being the unit vectors, second row being the partials, and the third row being the components of the vector field f. And so here, for instance, if you take the determinant of this matrix, 3 by 3 matrix, the x hat component will be the term that you see here. This is the y hat component, and this is the z hat component. And so all we need to do is to take the partial derivative with respect to y minus partial derivative with respect to z. And if you take these partial derivatives, we end up with the expression that you see here for the x hat component. This, when you take the partial derivatives, gives you this term, and this gives you this term. Alright, so let's go back and revisit a problem that we discussed in Lecture 21A, where we're given a 2-dimensional vector field. The vector field had this form, x minus y, x plus y, and this is linear in x and linear in y, and so typically it's usually quite nice to start with linear problems because it has it's well-behaved function, and so that's why we started with it, just to gain some intuition as to what we meant by divergence and curl. So in a 2D case, the divergence, basically, we can sort of mimic a 2D problem starting with 3D, but in this case, the vector field we know only has an x and a y component, and that the x and y components can only be functions x and y. So this is sort of a simple way of cheating a system that basically is written 3D to actually represent a 2D problem. So if you basically carry out this operation on this vector field, we end up with just df partial x plus dg partial y. On the other hand, for the curl, again, similar idea. We write this in determinant form, partial x, partial y, and partial z. Again, the x, y, and z components are shown here to essentially mimic that of a two-dimensional field, even though we've written in 3D form. If we do this calculation, we'll end up with an expression of this form with z hat. But in 2D, of course, z hat doesn't exist. And so what we do is we assume it's an imaginary axis, and we call it a vector, a unit vector j. We'll discuss this a little bit more in the subsequent lecture. We also said that we could basically take this vector field and describe it in terms of two components, one which we attributed to a flux and one we attributed to circulation. So this one would essentially be one we associate with a source. That means fields appear to be radiating outwards from a point, and this would be essentially rotation. So essentially field lines that appear to be rotating about an axis of rotation. So what we're going to do now is basically take this field example, apply the divergence, apply the divergence with respect to the flux and divergence with respect to circulation. Again, this is a reminder of what we meant by F flux. This is what was meant by F circulation. And if we go through this procedure, we end up with a 2 for this one, a 2 for this one, and a 0 for this one. This would be essentially applying the divergence operator to the total field, the flux field, and the circulation field. Correspondingly, if we apply the curl to the vector field, curl to the flux component and the circulation component, then we end up with 2z hat, 0z hat, and 2z hat. Now recall, again, as I mentioned just previously, the z hat basically does not exist in 2D. We're just saying it here because we did actually perform this as a form of 3D calculation. But in actual fact, in 2D, this would be represented by an imaginary pseudo vector, typically j. All right, so here I've put everything in table form. So here is the definition that we've got now for divergence of vector. This is the definition for the curl of a vector. The divergence vector for a 2D has this form. This was the definition. And for 2D, the definition for curl vector had this form. Of course, it's this z hat in 2D would become equivalent to j, which is sort of a pseudo vector pointing in the same direction as z. This would be the calculated value from the previous lecture for the magnitude of circulation over area. And this is the calculated value for flux over area from the previous section when we were dealing purely with 2D fields. So if you go back and look at the results, we essentially, for these three field components, we end up with 0, 2, and 2. And now if we apply the actual formal definition for divergence, lo and behold, we have the same results. Similarly, for the curl of a vector field, magnitude circulation of area was 2. This one was 2 and this one 0. If we look at the curl of the vector field, which now also implies that there is a vector associated, but we call it a pseudo vector, we get 2z hat and 2z hat. This being the magnitude, this is the actual vector. Notice the magnitude 2 here, it's equivalent to 2 here, 2 is equivalent to 2. So effectively, it looks like our intuition regarding these definitions seems to have borne out, and now we have two types of operations can be applied to any generalized vector field. So in conclusion, the divergence operator picks off the source, which is a flux type behavior of the vector field, and the resultant is a scalar density representing the properties of the source with units of flux over area. On the other hand, the curl operator picks off the rotation or circulation type behavior of the field, and the resultant is a pseudo vector representing the axis of rotation and with a magnitude having units of circulation over area. All right, so the last topic would be just looking at vector identities involving operators, and I basically have shown There are various other types, subtraction, multiplication, matrices, and so on, but A plus B is a simple operation. This is the operator positive, takes two vector fields and adds them together and produces a third vector C. We also have the gradient of a scalar field. This is the operator. It operates on a scalar function to produce a vector valued function. The divergence operator operates on a vector field through a dot product. So it takes this vector, applies a dot product on this vector to produce a scalar function, which is this that you see here. This is, of course, here we're representing in 3D rather than 2D. And the curl basic involves the cross product symbol operating the del through a cross product operating on a vector field A. And the resultant is basically it produces a new vector field. And so this is just showing how basic cross products, how a curl is computed using the determinant formulation. We end up with a new vector field, and we're going to call this a vector field F. All right, so let's look at some vector identity examples. So for example, if I took the divergence of a curl of A, this is equal to 0. So that means this field here, if the divergence of the field is 0, which means it's a source-free field. A basically has three components, x, y, a, z, and so what we want to do is to prove that this is correct. So we take the symbol for the operator del, which is this one. We take the curl of the vector field A, and this is the vector you get, and then we apply the dot product between these two. So this partial x operates on the x component of this field, y operates on the y component of the field, and z operates on the z component of the field. If you basically carry this through, we end up with the 6 terms. And you'll notice here that we see pairing. We have second derivative of a of z dx dy and second derivative of az dy dx. But if az is well behaved, then whether or not you will take the partial derivative with respect to y followed by x or x followed by y is immaterial. They essentially give you the same result. So you have cancellation between this term and this term. And similarly, you'll see pairings, dx dz and dz dx, and dy dz dz dy. So if you add these 6 terms up, essentially end up with a value of 0. So that effectively tells us that a field of this form is a source-free field. Let's take another example. Take the gradient of a scalar field, and then we take the curl of this. We're going to say that this is a rotation-free field. If there's no curl, if you end up with 0, that means there's no rotation. All right, so we're going to basically just apply the determinant formulation for taking a curl of a vector field. So we're operating on the gradient, and the gradient would just be taking the gradient operator operating on the scalar function. This is the x, y, and z component of the field. If we then carry this out, then we end up with this being the x component, this the y component, and z component. But again, notice that we have dy dz or dz dy. The order of differentiation doesn't matter. Essentially, this result will be 0, this result will be 0, and this will be result will be 0. So effectively what happens is we basically end up with a vector field which is 0. So that effectively says that if the field can be represented as the gradient of the scalar potential, then that field is rotation free. So these are 2 important identities that we're going to make use of very frequently. Another one is this one shown here. That is, if I take the divergence of the gradient of a scalar field, right, and I'll end up with a scalar Laplacian, which takes on this form. And if you look here, for instance, the divergence, here's the divergence operating on the gradient. Now if you carry this out, you end up basically with the second derivative of phi with respect to x, second derivative with respect to y, second derivative with respect to z. And we can also represent this as del squared, which is a shorthand form for writing out an expression that looks like this form, and we call this the scalar Laplacian. All right, so here are another number of vector identities. This one we call a vector Laplacian, or Lagrange's formula for del. So what we have is this vector identity that says if you take the gradient of this divergence, which is a scalar function, minus the curl of a vector field A, that's equivalent to the vector Laplacian, which is del squared A, operating on a vector field A. So let's look at each of these term by term. Let's do divergence of A. So there is the del operator, a dot product operating on the components of A, which is x, y, ay, az, and we end up with this expression that you see here. Now what we do is we take the gradient of this expression, which is what you're shown here. This is a scalar function. And so that means we're going to take the derivative with respect to this expression with respect to x, which becomes the x component of the vector field. All of this with respect to y becomes the y component of the vector field. Everything with respect to z becomes the z component of the vector field. And so essentially what we see is when we take a derivative with respect to x, here's the x component of the vector field. Derivative with respect to y is the y component. Derivative with respect to z is the z component. All right, then we take the second term, which is del cross A. We know what del cross A is. We can basically do that as an intermediate calculation. That's the expression that you see here. And now we apply the curl on this vector field. This is just going to be basically computational bookkeeping. And so if you go through the process, you'll end up with this as the x component for the resultant of curl cross A, of curl of A. This will be the y component, and this will be the z component. And now what we do is we take this expression, combine it with the expression, which means it's just subtract the two, which is what we've done. And you can go through that as an exercise. We end up with this as being the x component, y component, z component of the final vector field. But notice here that effectively we're essentially having the same form for the x, y, and z component, and the only difference is that for the x component, the a value is the x component. For the y component, a is the y component, and for the z, it's a of z. So we can write this in compact form as just del squared a, which is this second derivative operator that operates on all three components of the vector field to produce this vector field. All right, so this basically concludes Lecture 21B. Thank you for listening.